Hello, I'm Mike Sample, the CTO at CMD. Today I'm going to talk about using Linux sessions to monitor and review Linux workloads. Most of the world's servers run Linux, and virtually all of them are maintained using a command line interface by members of the dev, DevOps, and SecOps teams. This presents an insider threat risk. Someone could be accessing or exfiltrating customer data in the production environment. Modern approaches to infrastructure prohibit direct access to production environments by the dev and DevOps teams. Instead, they have indirect access by submitting source code and configuration changes to a source code repository. These submissions are peer-reviewed for correctness and security. However, even with this improvement, Linux sessions need to be monitored in production. The applications used by customers run in Linux sessions, and SecOps may still need command line access. In this talk, I'm going to present the fundamental aspects of measuring Linux workloads, define Linux sessions, and introduce some session classifications that are valuable for security and monitoring tasks. The Linux workload model comes directly from Unix. This is my copy of Kernighan and Pike, which was published in 1984. The text snippet shows the same fork and exec system calls used to launch programs on Linux today. The setsid system call, which creates a new Linux session, was introduced in 1989. Recording a workload should capture who did what, when, and where. When you log in with the command line to Linux, you are presented with the terminal view similar to what's shown on the right. It echoes back the commands you type into it, and it may show you the output of the programs those commands execute. In this example, I changed the directory to the source directory, ran make-s, and then exited the session. The -s is for silent mode, so make-s is really the tip of the iceberg for what could be going on. It could simply be building some software packages, but it could also be installing malware, exfiltrating data, and tainting your software supply chain. Now we'll examine the who, what, when, and where of Linux workloads. Note that if you are recording these workloads in a central repository, the server identity of where the actions took place must be captured. Also, the Linux process identifiers are reused and must be qualified with additional information to maintain their uniqueness in this central repository. To the Linux kernel, user identity is presented by integer IDs. And even then, the kernel only really cares if you have UID 0 or non-zero. UID 0 is the root user or super user and has unlimited privileges. Names are associated with user and groups IDs with etc password and etc group files, as well as the pluggable name service switch, which could, for example, access a central user directory through LDAP. There are two challenges today with the traditional Linux user model. The first is that containerized workloads often run in user namespaces and use a different range of user IDs. When observed from outside that namespace, the user IDs do not match any entries in etc password. The second challenge is that the traditional model of having unique Linux username and group and credentials for each human user is being eroded by newer host access methods such as SSM and kubectl. These tools use the same Linux user for all accesses. Where? Schedulers like Kubernetes use a pool of Linux servers to run various containerized workloads. The scheduler usually doesn't care which server is used for containerized workloads, so long as it has the CPU, RAM, and other necessary resources available. This presents a disconnect between monitoring the server workload and being able to identify the individual applications. The same server could be running 25 instances of Nginx in different containers. And the way you find out that it was the staging instance of your sign-up application is by recording additional metadata, such as the container image identity and version, and the Kubernetes cluster namespace and pod names. When? Capturing the Linux system clock in UTC, along with the kernel's boot ID to assist in clock reset situations, is a good start for capturing timestamps. Also, capturing the event write or processing times at a centralized workload repository can assist in detecting large clock skew situations. As with user IDs, the new Linux time namespace makes it important to understand the ramifications of which time namespace the system clock is being observed from. What? Processes, files, network, and inter-process communication. Processes are the embodiment of running programs. A Linux server may execute millions of programs per day. These processes may touch files, use the network, communicate with other processes on the server, and may change the configuration of the system and hardware. By capturing an accurate version of these events, one may see the possible paths of data flow in the system. For example, one could capture that a process had the etc shadow file open for reading at the same time as it had a connection to a remote IP address open, and therefore the contents of etc shadow may have flowed to that IP address. I lied a bit when I said terminal output cannot accurately capture a Linux workload. You can capture some of it if you run the ps command in your terminal to show all the running processes. The venerable ps command was documented in Kernighan and Pike in 1984, as shown in the text snippet. The terminal output on the right shows all the running processes on a very lightly loaded Ubuntu Linux server. Even on a lightly loaded server, there are a lot of processes and much information to be reviewed. PSAJXF piped into awk is one of my favorite commands. Awk is also documented in Kernighan and Pike, so I guess I like vintage programs. Here we use awk to reduce the noise by filtering out kernel threads. This leaves the Linux services started by the init process and my SSH session. If you look a bit more closely, the purple highlights show 4 related sessions. Starting at the bottom with my SSH session, its SSH connection processing parent session above it, the main SSH server listening for new connections above that, and finally the init processes session. We'll look at this a bit more detail in the next slide. This is the PS and awk output from the previous slide, with some sessions removed so that only those related to my SSH login are shown. Starting at the top, highlighted session, we can see the init process running sbin init, which is a symlink to systemd. This process is started by the kernel when it boots, and its job is to start up all the configured services. One of those services is sshd, which listens on TCP port 22 for incoming SSH sessions. SSHD is the second session down, and we can see that its parent PID is PID1, and that of the init process. Therefore, its parent session is init session SID1. The third session down is comprised of 2 processes created by SSHD to handle my specific SSH connection. And finally, the bottom session is my login shell that was created by its parent session. It has 3 processes in it, 2 of which are for the PS and awk programs. Note the process group ID, or PGID, of PS and awk is the same. This is important for signaling and job control. Special sessions. There are some special sessions. The init session, as discussed on the previous slide, is started when the system boots. It is the ancestor of every other session on the system. Host access sessions permit command line access to the server over the network and by directly attached terminals. Host sessions can be identified by their executable name, such as SSHD. Individual host access sessions, such as an SSH login, appear as children sessions of the host access session. agetty, which handles terminal and console logins, is an exception to this and reuses agetty's session for the login shell. When this user logs out, the Linux session is ended and a new one is created for a new agetty. Special sessions, Tmux and Screen. Tmux and Screen are special programs that protect command line sessions from being automatically ended if you log out or a network issue breaks your connection to the server. DevOps folks will often use these to protect complex administration and troubleshooting tasks, and to allow these sessions to be accessed by other users or later in the week. Tmux and Screen sessions will reparent their sessions to be children of the init session to accommodate the loss of the host access session instance in which they were first created. Special session features. Controlling TTY may be associated with a Linux session. Their presence suggests that the associated session's purpose is for interactive command line use by a human. Finally, if we take into account the special sessions like init, host access, Tmux, and Screen, as well as the presence of a controlling TTY, we can divide the sessions into some useful classifications. First, host access enabling sessions, identified by their executable name, should be carefully enumerated for security purposes. These are the doors into your Linux house. Note that even if these sessions match aspects of the 4 quadrants, we consider host access sessions to be unique and not part of those quadrants. Host access sessions include SSHD, Amazon SSM agent, and the kubelet plus cryo, as well as agetty. In the case of agetty, it will transition from a host access session to the lower left quadrant when it execs login. Second, the upper left quadrant, representing instances of host access, including an associated controlling TTY, should be carefully scrutinized for insider threat purposes, as there is typically a human associated with them. The upper right quadrant represents some non-interactive remote access, such as using SSH to run a command instead of creating a login shell. Often this type of session is used by automation tools such as Ansible, but humans may use it as well. Ideally, separate Linux usernames are used to discriminate between automation and humans to permit more careful review of human access. The bottom left quadrant generally represents shells running inside Tmux Screen and from terminal access. Any other matches should be examined as well. The bottom right quadrant represents services started by init or those that have reparented themselves to the init session, like the non-interactive main Tmux and Screen processes do. The services portion is important to monitor, as this is typically how applications such as web servers run, and where application security exploits may provide a means for attackers to gain access to the system. These are the windows to your Linux house. These classifications help tailor the type of monitoring and indicators of compromise to watch for. They can also help in selecting which workloads to record depending on your threat model. Today, we covered a model for how one can accurately describe Linux workloads using users, groups, timestamps, host names, and container metadata, processes, file access, network access, and inter-process communication. We defined the Linux session as a group of related processes initiated by the setsid system call by the session leader process. And finally, we classified Linux sessions to focus, review, and monitoring into the following: services that can be web applications with application security concerns, human access for interactive command line use, including Tmux and Screen shells, non-interactive host access by humans and automation, and the sessions that provide host access itself, which should be enabled according to policy. Thank you for following along. I hope this has given you a clearer understanding of Linux, workloads, and sessions.